Hello, and welcome to the presentation of the paper, Clock Synchronization over Networks using Sawtooth Models. My name is Pol del Aguila Pla, and I work at the EPFL and the CIBM in Lausanne, Switzerland. But this work was done while I was doing my PhD at the KTH Royal Institute of Technology in Stockholm, Sweden. Without further ado, I get into the topic of the presentation, which is clock synchronization. And basically what we do in our work in clock synchronization is to use new hardware designs specifically tailored to improving ranging and synchronization in wireless networks, analyze them rigorously mathematically by characterizing their identifiability and estimation theoretical properties. So in specific, in this paper and in this presentation, I will discuss an introduction to the Sawtooth model for clock synchronization, speak about Kramer-Rauer bounds related to this model, and present some very basic estimation techniques for Sawtooth signal models. And after which, I will be able to show you some results on clock synchronization using this model. So my collaborators in this project were Joakim Jaldén, Lissy Pellaco, Satyam Dwivedi, and Händel. And basically the project started when in 2013, part of our group developed specifically tailored hardware to improve ranging accuracy in wireless networks by round-trip time measurements. So the improvement basically is that each of these nodes, which is not standard, it includes a time-to-digital converter in order to measure time more accurately. This, in turn, leads to a low communication overhead in the round-trip time protocol, because this accurate time calculation allows you to, instead of sending pulses loaded with time information between nodes in a network, sending simple pulses without any information. So it lowers the communication overhead. It lowers the power consumption because now only the clock of the TDC, the time to digital converter, needs to go fast, and it's specifically designed to only count time, and therefore it consumes less power than a CPU going at the same speed. And it has a higher measurement accuracy. And as a quirky detail that will prove to be very important later, nodes with this scheme can measure their own clock period and therefore know their true clock period, not specified by the manufacturer. So to introduce a bit the notation, the nodes M and S will be carrying an RTT measurement protocol and sending ping and pong pulses, ping and response pulses between each other, and their periods and phases will be noted like so. In the continuing of the presentation, we will assume that M's phase is 0 because it has no bearing on the results. So here is an illustration of the round-trip time measurement scheme that is proposed with nodes designed as specified above. And basically, what happens in this scheme is that M sends ping pulses every sampling period, which we assume to be a multiple of its own clock period, which again, it can measure because of its TDC. Then when S receives its pulses, it cannot immediately act on them because it won't notice it has received that pulse until its next clock upflank. The TDC, of course, of S will have recorded the entering pulse, but S itself, the CPU, won't be able to decide on how to proceed based on that. So after reaching the next clock upflank, S will introduce a delay that we assume known of delta 0. And after that delay, it will respond with a pong or response pulse. And then the TDC, M's TDC, will measure the time since the sending of the ping pulse until the reception of the pong pulse. We can see here in the scheme already, if we are perceptive, that the different measurements are not equal as we would expect from a round-trip time measurement scheme. And this is because this time between the arrival of the ping pulse and the next clock upflank varies with time. So this variation, we were able to derive a model for this variation, and it turns out that this delta n can be expressed in terms of a mod function. It depends on the sampling period. It depends on the clock speed of the node S, and in the difference between the frequencies of the node S and node M, of their clocks, of course, and also on the phase of node S. So immediately what we see is that this is empirical results obtained from an actual implementation of the nodes that we described at the beginning. And we see here that if we were able to recover the parameters, like the ranging parameter between the devices, S's clock period, which shows up also here in the frequency difference, and this parameter, for example, the phase of S's clock, we would be able to synchronize the nodes, basically. So the problem, of course, is that the measurements are noisy and they're not clean as specified in the previous model. And in order to portray that situation, we write the generic Sawtooth model like so, where here we have an amplitude parameter alpha, an offset parameter alpha, an amplitude parameter psi, a frequency parameter beta, and a phase parameter gamma. And we allow for two distinct white Gaussian noises, W and V, one inside and one outside the nonlinearity. For more details on the derivation of the model or the inclusion of these noises, an estimation theoretic analysis, and conditions for the identifiability of the model, we have this journal paper, which is currently uploaded already to the IEEE Explorer, and it has exhaustive empirical results on the system we propose here. But the main point you have to know about this paper is that the model specified like so is identifiable, provided that the two noises here present, one inside and one outside nonlinearity, are active. For more information, kindly click on this link. What we do in this paper is to provide something beyond this theoretical guarantee that the model is identifiable. And we do that by providing some kind of performance references for this model. So first in the form of a estimation lower bound in a manner, and second in the form of estimation techniques and an empirical evaluation of how well they work. So the problem we have in order to derive Cramer-Rao lower bounds or equivalent bounds on the performance of estimators for the clock synchronization parameters is that our model is not differentiable in many points. Every time there's a jump in the mod 1 linearity, it's not differentiable. So in order to circumvent this problem, what we do is we work on an unwrapped or linearized model of Z. We call Z, sorry. And basically what we do here is we remove the mod 1 nonlinearity, shown now in red, and we use the assumption that the time it takes for the ping pulse to travel and the pong pulse to travel is the same. And in that manner, we obtain this other model, in which basically you can see that the two noises that were previously inside and outside the nonlinearity now get combined into a single noise, UN, which has a standard deviation that is related to both of the standard deviations of them shown before. So what are the caveats of this approach? It's clearly, if we analyze the model for Z, we're not analyzing the model for Y, but it provides a linearized intuition, as we will see in the empirical result. Also, in this new model for Z, the phase of S's clock and the ranging parameter are not jointly identifiable. But we can go around that also by supposing we know the respective order when deriving the bound for one. So in any case, it provides a lower bound that is too low but it still provides lower bound in a way. And then the third issue is that the standard deviation of the noise in the model for Z depends in one of the parameters to be estimated. But luckily, this is actually covered by standard results on multivariate Gaussian models. And so we were able to derive the Kramer-Rao lower bounds without much further complication, except the technical details of the derivation, which you can see in the paper. Further on, what we do is to design simple estimators for the parameters of a generic Sawtooth model, which we constrain with two key things that we know that happen in clock synchronization. So first, we know that the amplitude is negative. If you want to revise the previous formulas of the models, you will see that it had a minus period of SS clock acting as an amplitude. And therefore, we know it's negative. And then we also know that the amplitude is actually known when the frequency is known. These are two specific characteristics of our clock synchronization problem that affect the Sawtooth signal model that we obtain. So the simplest of the methods that we propose is the periodogram and correlation peaks, which we call PCP. And basically what it does, it takes the signal, it zero pads it L minus 1 times, it removes the mean, and then it computes a periodogram, so the square of the DFT of this zero padded, zero mean version of the data. And it uses that to estimate the frequency parameter. So here you can see an example of a power spectrum estimation for the signal. And basically we would choose this location divided by the number of samples of the zero padded signal as an estimator of the absolute value of the frequency. So the next step is simply to build two single period templates. So a template of the first period of the signal given the estimate of the frequency that we obtained. So one with positive frequency and one with negative frequency to try to disambiguate which one was the one that created that peak. And then we take those template signals and we take the first estimated period of the signal. We max normalize everything and zero min it. And then we do a circular correlation between these template signals and the first period of the signal, of the observed data. And this allows us to first distinguish. So clearly here in the left, we see that the slope of the template is not the same as the slope of the data. And this will yield not only an estimated delay that is completely irrelevant, but also a correlation that will be much lower, the maximum of the correlation. While here, the slope of the template and the slope of the data are the same, and therefore the correlation will reveal that the estimated delay and therefore the estimated phase can be obtained by this simple method. So then the final step is simply supposing that the estimates for the frequency and phase are correct. We said that we know that the amplitude is known when the frequency is known. Then what only remains is the offset parameter, right? So in these conditions, if we assume that all our estimators are correct, then we can derive the closed form minimum mean square error solution for the prediction mean square error. So basically, this simple method is the PCP, and it has a very good advantage. It's that it's very, very fast to compute because it only requires a simple DFT, because basically the next steps use computations in sizes much smaller because they just use the first period of the signal. And then a simple sample averages here. So it's very light computationally. The next method we propose is grid search. So basically you define the grid on the range of valid parameters. So -1/2 to 1/2 for the frequency and 0 to 1 for the phase parameter. And then you simply pick the grid point that yields the lowest prediction mean square error according to the model. Here, alpha hat, beta, gamma is simply the closed form solution we mentioned before, when you assume that beta and gamma are correct. And psi hat beta is also the known amplitude once you know the frequency. Here you can take two flavors. So you can basically choose the grid as a global grid on the whole range of parameters. And then the result is that you get a very irregular function landscape, and that many of the grid points that you chose are actually wasted in irrelevant areas of the parameter space in which we shouldn't be searching. Here we can see that there are even irregularities, even if they're not apparent in the large scale in the function of gamma. But the other alternative is that you can choose a local grid around the solution of the PCP, and you expect to have a smoother behavior there if the PCP was reasonably close to the right solution. And of course, by using the same computational resources, your gridding is finer because you're just looking at a small neighborhood around a plausible good point. So both these methods, we've implemented them, and the implementation is available in the GitHub repository, which you'll see again at the end of the presentation. And we tested them in some Monte Carlo repetitions of generations of the model. So here we can see that both estimators have a behavior in terms of convergence with the sample size pretty similar to the Cramer-Rao lower bound we derived for the Z model. Here we are seeing the estimation performance of rho, which is the ranging parameter related to this time of going and coming back through the speed of light, of course. Then we also see that we achieve resolution of centimeters in, or tens of centimeters in ranging, although we have to be cautious because our noise assumptions have been pretty relaxed because we were simply trying to characterize the behavior of the model. For a more thorough analysis, as I said before, you can see our journal paper in the Open Journal of Signal Processing. Then in terms of more interestingly, the estimation of the frequency parameter, so the main synchronization parameter here, we see that the PCP has quite erratic behavior, although the envelope is efficient. It converges with n towards a lower error. It has a bumpy behavior, which is probably caused by the bias introduced by the gridding used in the FFT, whilst we see that the local grid search around the PCP point actually achieves to avoid this bumpy behavior. So basically what that means is that even though these points proposed by PCP have increasing errors in these bumps, they're not too far away from the optimal point, which the grid search is capable of capturing. And overall, although it's not exactly the same rate of convergence, we can say that it's an efficient estimator, the local grid search around the PCP point. Whilst for the phase parameter, the situation is quite more complicated. We see that the PCP also behaves erratically, which we believe is mainly related to its erratic behavior for the frequency estimation. And the LGS is capable of correcting that, but up to a point only. And clearly here, the rate of convergence with the sample size suffers a bit more than it did in the estimation of the frequency. So for more details on the empirical evaluation of this methodology, which we think it's a very important thing to provide, both performance references in terms of Cramer-Rao lower bounds and mean square error of simple estimators, in order for this technology to continue moving forward and for people to design better estimators for these parameters. So that is all, and please visit our GitHub repository to see all the code used to generate the figures in this presentation, and access our paper, which is currently open access during the duration of the conference, at this address too. Thank you very much for listening.